Okay, so we are streaming live on YouTube now, so anyone trying to watch there should be able to see it now. I'm going to give it 45 more seconds for our very punctual folks to show up before it turns to 8:01. All right, with that, let's go ahead and get started. Thank you so much to everyone for joining. It is Tuesday, March 28th, bright and early, 8 a.m. Hawaii time. We are holding a press conference at the 20th meeting of the JWST High Energy Astrophysics Division. I'm going to be your host today. My name is Kerry Hensley, and I'm the JWST Deputy Press Officer. I'm joined by Megan Watsky, the Press Officer for the High Energy Astrophysics, as well as Frank Reddy from NASA Goddard. We're going to be hearing from 5 presenters today about the superlative gamma ray burst 221009A. Among other things, I look forward to learning how I'm actually supposed to say that. And this gamma ray burst emission swept through the solar system last October, and since then, researchers have been hard at work kind of deciphering that emission and learning about this superlative event. So I'm going to briefly introduce our presenters. We'll then hear the 5 of them speak in order. We're not going to break for a Q&A in between their presentations, but we'll save plenty of time for your questions afterward. So for all of our offsite journalists watching on Zoom, go ahead and use that Q&A feature to queue up your questions. Please be sure to identify yourself, give your name, your affiliation, and if applicable, who you want to direct your question to. So our presenters today in order will be Eric Burns from Louisiana State University, followed by Kate Alexander from the University of Arizona, then Andrew Levan from Radboud University, Sergio Campana from the National Institute for Astrophysics in Italy, and finally, Michela Negro from the University of Maryland in Baltimore County. So with that, I'm going to go ahead and turn things over to Eric for our first presentation.
Okay, so thank you, Kerry. As introduced, my name is Eric Burns. I'm an assistant professor at Louisiana State University. And I'm going to introduce the gamma ray burst 221009A, which has been called the BOAT for the brightest of all time. This is the night sky in optical. This is the form of light that your eyes can see. You can see our gorgeous home galaxy, the Milky Way, laid out across the center. At higher energies, the highest energies we have, this is the gamma ray night sky, where you can still see the Milky Way, but it looks a little bit different given that you need kind of rare sources to produce light at these energies. So gamma ray bursts, they come from three sources. The one of interest today comes from the collapse of massive stars. So you have the core collapse. This creates a black hole. The black hole powers jets that propagate out at just under the speed of light. As these jets go out, they release their energy in the form of pumped gamma ray burst emission. This is followed by what's known as afterglow. And at later times, the energy deposited into that star powers a supernova explosion. So these three phases, prompt, afterglow, and supernova, will be the focus of the first three talks. So the prompt signature, we observe them like this. You have these bursts of gamma rays over time. And this GIF is going to step through some of the interesting bursts seen by NASA's Fermi Space Telescope in 15 years of observations. Each one is about 10 times brighter than the last. Each one is extremely interesting. We've done many analyses on them and learned a great deal about gamma ray bursts from these. And this one is the previous record holder for brightness, now compared to what we had last October. So we knew immediately we had the brightest one ever seen at Earth. But we realized that it was so bright, it actually blinded most observing instruments. So in Fermi, with work led by a graduate student named Stephen Lesage, we have reconstructed the actual brightness of this burst. And it looks like this. So comparing it to the other gamma ray bursts, we've observed these for 55 years. The one in red is the second brightest ever seen. So it is just an absolutely monstrous burst. It is extremely extraordinary. We've never seen anything remotely close to it. It was so bright that it was actually detected by instruments never designed for this purpose. The first signal came from interstellar space being detected by Voyager 1. As it propagated through the solar system, past the gas giants, it arrived at ESA's Gaia, and then integral satellites. It continued propagating, coming by Earth, being detected by Fermi and GRB alpha. It also affected Earth's ionosphere. It continued on to the Wind and the ACE spacecraft before our last signal from the orbiters around Mars. So the next question we had was, how does this compare to the bursts that we've seen? So in blue, this is a measurement of the brightness of gamma ray bursts seen over 50 years. The x-axis is a measure of the brightness in log scale. And you can see here that the boat is just, again, an extreme outlier. The Fermi analysis, we had to reconstruct our data. But by comparison to the results from Russian scientists working on the CONUS instrument on board Wind, and Chinese scientists using data from InSight and GECAMC, all three groups independently arrived at the same value. So we're certain in this result. We can overlay how often we get bursts of a given brightness at Earth. And the previous record holder in 50 years is between once per decade and once per century, and that makes sense. We can step out to more extreme timescales, ultimately ending on the fact that the boat is a once in 10,000 year event. So there's a reasonable chance this is the brightest gamma ray burst at Earth since human civilization began. So as the prompt emission swept by us, NASA's Swift satellite was behind Earth, so it didn't see it. As it continued in its orbit, it recovered the afterglow emission and provided the precise localization to astronomers around the world. So a unique event, we have basically the full capability of our astronomical resources to use. In the end, it was seen by more than 24 satellites around 3 planets and even one in interstellar space. And telescopes on all 7 continents, including results that won't be covered here, For example, the highest energy photons ever seen in a gamma ray burst by LASSO. So I'll conclude just by mentioning that there's only 5 of us here, but we are representing the work of several hundred scientists. This is truly a major international effort. So with that, I will close and I will hand things off to Kate Alexander.
Thank you, Eric. Hello, everyone. My name is Kate Alexander. I'm an assistant professor at the University of Arizona, and I'm going to tell you today about how studying the jet and afterglow of this extraordinary GRB are revolutionizing our understanding of the physics behind these extraordinary explosions. And I will also attempt to answer the question, why was this particular gamma ray burst so extremely bright? So we think that most gamma ray bursts are produced when a massive star ends its life in a supernova explosion. When the massive star explodes, its central core collapses to form a new black hole, which can power narrow streams of particles out of the star and accelerate them to nearly the speed of light. As these jets spread out into space beyond the star, the jet of particles will interact with its environment, producing what we call the afterglow, light that glows across the entire electromagnetic spectrum, from radio light to the visible light that our eyes can see, to X-rays and gamma rays. This afterglow phase lasts longer than the prompt emission, allowing astronomers plenty of time to study the jet in extraordinary detail and understand more about the physics powering it and the black hole that is responsible for launching the jet. Astronomers used telescopes all over the world and in space to study the afterglow phase of this GRB and learn more about its jet. In particular, 3 NASA missions that were used in the study that I was involved in, the SWIFT satellite, NuSTAR, and Fermi, which observe in X-rays, ultraviolet, and gamma rays. We also used radio telescopes on 6 different continents, some of which are shown here. I also want to highlight again, as Eric said, that this is one piece of an international effort by multiple teams. I've included some links to some of the papers that studied the jet and afterglow of this GRB specifically below, and some of them are also going to be available in the focus issue of the Astrophysical Journal Letters that's going live at the same time as this event. So what did we learn when we studied the afterglow of this GRB? We heard from Eric that the gamma rays in the prompt phase were extraordinarily bright, but how does the afterglow compare to the broader population of gamma ray bursts that we have observed previously? Well, first we looked in the X-rays. This shows here how the brightness of gamma ray bursts in X-rays fades away as a function of time. When we add this new GRB, the boat, to this plot, we see that it also has an extraordinary X-ray afterglow. This GRB has the brightest X-ray afterglow we've ever seen in any gamma ray burst. However, surprisingly, when we go to the other end of the electromagnetic spectrum and look at how this GRB's afterglow appeared in radio light, we find that it actually was not that extraordinarily bright. In fact, GRB 221009A was one of the fainter gamma ray bursts in radio that we have ever seen. And so this interesting juxtaposition of how you get an afterglow that shines brightly in X-rays and not as bright in radio is testing our physical understanding of the process for launching this jet and producing the afterglow light. You can see this when you look at all of the light we observed in the afterglow phase all together. So this plot shows the radio light, the visible light, and the X-rays. We've been observing gamma ray burst afterglows for 25 years, and we've developed a set of standard models that describe these afterglows really well and allow us to understand their physical properties. When we try to apply the models to the afterglow of this particular gamma ray burst, we find that they explain the visible light and the X-ray light quite well, but they cannot fully explain the radio emission. Instead, the radio light is dominated by another component that we still don't fully understand, but which we are very excited to continue to observe and uncover more deeply so that we can learn more about the physics and structure of these jets. So what have we learned so far from studying this afterglow of this gamma ray burst? And can it tell us anything about why this gamma ray burst was so bright? Well, first of all, we learned from this modeling that the jet of this gamma ray burst is actually not unusually powerful. When you compare the energy in this jet, it's very similar to the energy of jets we've seen in other GRBs. So then why was it so bright? It turns out that all of the energy in this jet was focused into a very narrow angle. So all of the particles moving in this jet were very extremely narrowly beamed, and that narrow beam happened to be focused right at Earth. You can think of most gamma ray bursts as the garden hose on the left, where they spread their particles and their energy over a wider angle. So if you're thinking of being a flower in the garden, you don't receive quite as much water at any one location. But the boat is more like the picture on the right, where all of the water is focused into an extremely narrow cone. So if you are a flower, or if you are a observer, astronomer on Earth looking at this gamma ray burst, all of that energy is pointing right at us. And that is why the GRB itself appeared so exceptionally bright from our location. We were also lucky in that this gamma ray burst was fairly nearby to Earth as gamma ray bursts go, a mere 1.9 billion light years away. The final point I'd like to leave you with is that because of this gamma ray burst's location close to Earth and the extraordinary data set that astronomers have collected, we have a unique opportunity to test new physics with this event and improve our understanding of the universe's most powerful explosions. And now I'll turn it over to Andrew, who's going to tell us about the supernova phase of this gamma ray burst.
Thank you very much, Kate. I will take over. My name is Andrew Levan. I'm a professor at Radboud University in the Netherlands and also at the University of Warwick in the UK. And I'm going to move on to talk about some of the things we've been learning by using the James Webb Space Telescope and the Hubble Space Telescope to try and study this burst. And so we've heard from Kate and from Eric about the actual burst of gamma rays and its afterglow. And these are all related to this very powerful jet of material launched at almost the speed of light. But we believe that these gamma ray bursts are created by the explosions of very massive stars. And the debris and the remnants of those stars are also thrown out in this explosion. And we should be able to see these in the supernova associated with it. And the supernova is very important because the supernova ties back to the properties of the star. And so a key question, is this exceptional burst caused by some very unusual and rare star? As others have highlighted, this is a multi-pronged effort, and several different groups have used different combinations of data to actually undertake what's proved to be really rather challenging observations to try and understand this particular event. And so there's a few of those which are highlighted here using different data and trying to combine that to really get the best diagnostics that we can. And the basic principle which underlies searching for a supernova is that gamma ray bursts and their afterglows start bright and then fade away over the course of days to weeks. In contrast, supernovae start faint and then rise up on the timescales of days to weeks. And also, whilst gamma ray bursts emit their light across the electromagnetic spectrum, supernovae emit most of their light in the optical band. And so if one looks at the optical light of a GRB, one might see it slow or indeed reverse its decay as time goes by, giving a later time bump that we can identify with the supernova. However, while nature has clearly been very kind in giving us a 1 in 10,000 year event, it has not been kind in every single way. And when one wants to study the supernova in optical light, there has been the particular challenge that this burst came at us from a direction which was really quite close to the center of the galaxy. And so on the right-hand side here, you can see the projection of the line of sight to the burst through the galaxy. And then on the left-hand side, in the view from Earth, you can see also that it was in the plane of the galaxy in the sky. And so these dark patches are actually dust lanes in our own Milky Way. And we have to basically look through those in order to actually study the burst. And this is particularly acute in optical light. And we believe, for example, that only about 1% of the light which is actually emitted from this source is making it through the Milky Way to us. And this blank screen is in fact a beautiful James Webb image of a deep field, but only 1% of the light has come through. And we can get around that somewhat by moving into the near infrared, for example, at around 2 microns, where around 10% of the light comes through, then you can start to see something. But it isn't until one pushes out really into the mid-infrared, much further redwood of what we can see with the naked eye, that one starts to get a clear and unobscured view of this source. And this is one of the things which Hubble and Webb can do extremely well. And so in the near infrared, which is where the Hubble Space Telescope can look, this is what you see. These are observations actually taken 1 and 2 months after the burst. And you can see in the circle, there's a little dot. The burst has faded a huge amount, right, from when it was one of the brightest sources in the sky. And you can also see a little stripe that looks like it's going through the middle. That is actually the galaxy that this burst is coming from. And remarkably, it looks like an ordinary galaxy. So this exceptional burst is not coming from an exceptional place. And when we switch to using the James Webb, we can in fact go even further into the red than is possible from Hubble or from the ground. And so this is a spectrum where we've taken the light and split it into its component parts. And I've marked the visible, which we can see with the naked eye, and the near infrared, which is also accessible through the atmosphere. And the green line on here is actually a spectrum taken from the Very Large Telescope. It's a very important spectrum because it's the one which told us the distance to this burst, that 1.9 billion light years that Kate just mentioned. But it is limited because it can't go beyond that 2 micron mark, because there the atmosphere becomes opaque. You have to go to space. And so when we add in the abilities of the James Webb Space Telescope, then this actually gives you so much more space at wavelength range to use. And it gives you a much, much clearer picture of the physical processes which are going on. It's the real, we always talk about the size of the mirror, but one of the real advantages of the James Webb Space Telescope is that it can actually look so much further into the infrared. And what we expected to see in the optical light here is this bump from the supernova, this extra component. And it's very hard because we're only seeing 1% of the light, and different teams have to do different assumptions about this to make it work. But with the Webb data and with the Hubble data, we actually don't see any sign of a supernova. And you can see that the spectrum, the shape of the observations as seen by James Webb and the shape of the observations as seen from the ground much earlier are essentially identical. There is no sign of a supernova in these observations. And this is a surprise to us, and it's a puzzle. And so an open question for the future is just, where is this supernova? Is it a case that it is hiding in the glare of the gamma ray burst and behind the Milky Way dust? It's just hard to recover, but it's there. Is it not there because something strange is happening? For example, did the newly formed black hole, was it so massive, for example, in this particular case, that it swallowed the supernova before it could escape? Or is it not there even because this exceptional GRB, the boat, was not formed from the collapse of a massive star? Now, for the last few months, the position of the GRB has basically been behind the sun for optical telescopes. We haven't been able to look. But visibility is now opening up again. More observations, including with Hubble and with Webb, are going to be undertaken in the next few weeks and months. And so watch this space for what we hope will be a more conclusive answer. And with that, I will pass on to Sergio Campana from ENAF, who will tell us a little bit about why where this burst on the sky was not such a bad thing. Thank you very much.
Thank you, Andrew. Hello. Okay, I'm Sergio Campana. I'm a research director at ENAF Brera Observatory in Italy, and I will give you a brief outline of this burst from a somewhat different perspective. A gamma ray burst illuminates as a torchlight the full line of sight from the host galaxy to our own Milky Way. As Andrew showed before, the GRB afterglow was heavily absorbed by matter along the line of sight within our own galaxy. Light can not only be absorbed, but can also be scattered. Scattered means deviated. So in the Earth atmosphere, the sunlight can be deflected or scattered by icy crystals to form this beautiful halo of 22 degrees radius. The same effect works also for X-rays, but since X-rays are much more energetic than optical photons, here the process occurs on much smaller angular scales. So X-rays are deflected to less than 1 degree. And here you see what happens if the incoming light encounters a dust screen in blue. It produces a ring on the sky. a large one. And if the dust layer is further away, the green one, it produces a smaller ring. So these rings are informative on the distance of the dust layers, on the location, and also on the grain size. Do we see rings? Yes. If we have a bright X-ray source that turns on U, and if it encounters a large amount of dust within line of sight, we can have rings around the source. In this animation, you see what happens. There is the source that brightens up, encounters a dust layer, then second one, and when the light reaches the Earth, you see the source, the new source, and then two rings due to the two dust layers that expand with time. Now we come to the boat, and what we see here are the images taken by the SWIFT satellite, starting from day 1 to day 5. And you see the rings at different positions. If you make a movie of all these observations, these are real data, you have these rings that start small and then expand, and they start bright and then they fade away. These rings has also been monitored by the XMM satellite, which is an ESA mission. And XMM has a larger field of view and a larger effective area, so these data allow for a sharper view of the rings. Putting all these data together, we were able to locate them. So in these two graphs, you have the SWIFT view and the XMM view. On the abscissa, you have the distance from the Earth, and on the y-axis, you have the amount of matter. So any peak of these two graphs are dust layers along the line of sight. So there are screens that form rings. We were able to identify 21 rings. The closest one is 700 light years from us, and the further away is 71,000 light years from the Earth. So we are probing the structure of the galaxy along the line of sight, and the most distant one that has been observed by XMM is 71,000 light years from us. But since we are observing the gamma ray burst not exactly on the galactic plane, but at an altitude of 5 degrees, at this distance, the line of sight is about 5,000 light years above the galactic plane. And we do see some dust there. How is it possible? Because the galactic plane is flat, because our galaxy is somewhat warped in the outer edges. So we are looking at the galaxy through the burst through this warp. Summarizing, we observed the boat, and this allowed to explore the structure of our galaxy. We were able to identify 21 dust layers and work precisely the distance of these layers. We are now working hard to characterize the properties of this dust, and in particular the grain size of this dust and the chemical composition. From the first data, we can identify as graphite as the major component of this dust. And now I leave the stage to Michela Negro, who is going to talk about the polarization and multi-messenger properties of this burst.
Thank you, Sergio. Ciao, everyone. I am Michela Negro, an assistant research scientist at NASA Goddard Space Flight Center. I will talk about the polarization observations of the boat, but I would like to start with this very nice animation of a black hole. As we heard from the previous talks, the black hole is the final product of the collapse of a giant massive star. And we are all familiar with the idea of black holes as astronomical monsters that eat up everything that comes too close to them, including light. However, one question that we have been trying to answer for decades is whether or not black holes can return some power to the universe. According to some models, the answer is yes. The Blandford denial mechanism shows how a fastly rotating black hole threaded by a magnetic field, which is showing up in green in the animation, would work as an engine, transferring part of the rotational energy to create and power extremely energetic jets exactly like the ones that we observed for the boat. This mechanism also predicts that the jet would be mostly magnetically powered rather than powered by the material falling into the black hole, which disfavors the production of neutrinos. And this is in line with the observation of the IceCube South Pole Neutrino Observatory, which didn't detect any neutrino. This is a very nice example of how having continuous multi-messenger coverage can be crucial and informative even without a detection. Another prediction is the generation of ordered magnetic fields, which would in turn produce a highly polarized radiation. Polarization. The polarization is a characteristic of light that informs us about how the radiation is organized. In this animation, you have an example of a non-polarized light compared to a fully polarized light, much more organized, oscillating in just one direction. As of January 2021, we have a new satellite in space, the Imaging X-ray Polarimetry Explorer, or XP, which is devoted to the observation of polarization from astrophysical objects. XP measures a polarization of a particular kind of radiation that we call X-rays. These are the very same X-rays that we use to check for broken bones in our body. Now, high polarization from GRBs can be expected in the case there is a strong geometric asymmetry. This is happening in the case we are observing the jet from within, but really close to the edge, the jet itself. Another possibility is the presence of ordered magnetic fields that accelerate charged particles, and these charged particles would produce highly polarized synchrotron radiation. XP reported to the boat about 2 days after the initial alert, targeting therefore the late afterglow emission. But thanks to the dust cloud in the way that we just heard about from Sergio, XP was able to assess both afterglow polarization and the polarization of the prompt emission through its halos. From the low polarization of the afterglow, we learned that we are not close to the jet, the edge of the jet, which disfavor geometrical effects. This means that if a high polarization is observed in the prompt emission, this is caused by ordered magnetic fields, as predicted by the Blandford denial mechanism. For this event on a scale from 0 to 100%, the predicted polarization degree due to ordered magnetic fields ranges between 16 and 36%. The XP observation was unfortunately inconclusive. With a 2 sigma measurement, we could only set an upper limit on the polarization degree. However, we have a mild hint that Blandford denial mechanism is at play, bringing us one step closer to the answer to the question, do black holes return power to the universe? In the next future, we will work to combine all the pieces of the puzzle. Together with the XP and IceCube observation, we will have polarimetric assessments of the higher energy gamma ray radiation by the European integral. And as we've been stressing, we are only 5 of us here, but we represent a much larger group of scientists. We have this ambition project to put together all our data and work all together on a comprehensive multi-messenger, multi-wavelength study to refine the jet structure and energetics for this event and learn more about the physics involved. With this, thank you for your attention. This closes the set of presentations, and I open up the floor for questions.
Awesome. Thank you so much for those presentations. So with that, we're going to start the Q&A portion of the press conference. If everyone wants to go ahead and turn your cameras on. So for our reporters joining, please use that Q&A function to queue up your questions. And please remember to give your name, your affiliation, and who your question is for. You also have the option to upvote other people's questions if you want to make sure that they get answered. So I'm going to go ahead and let Megan read our questions aloud.
Great. So the first question is from Ethan Siegel, freelancer. It says, this question is for Kate Alexander. Hi, Kate. Do we have any idea why GRB 221009A's jets may have been so collimated relative to the other GRBs? Is it just serendipity that Earth happened to be right within the narrowest portion of this collimated jet?
Hi, Ethan. Great question. So the answer to the first part of your question is that right now we don't have a perfect idea of why this jet was exceptionally collimated, although as Michela mentioned, combining all of the observations together and continuing to study this jet as it continues to be detectable with our telescopes may give us the answer. It may have something to do with whether the newly formed black hole that we think launched this jet had particularly strong ordered magnetic fields or not. But the second part of your question also gets at part of the answer, which is that it is really exceptionally rare that Earth happens to be lucky enough to be right directly in the beam of a particularly narrow jet. So if you think of all the gamma ray bursts that we see, it's more likely we'll be in the path of one if it has a wider opening angle. So there may also be an observational selection effect in that most of the gamma ray bursts we happen to be able to see because we're directly in their path have a wider opening angle, and it's just extra rare to get one that is so narrow and also pointed directly at us.
Thanks for that. As of right now, there are no other questions in the Q&A. So I don't know, Kerry, if you want to ask anything or
yeah, I have a question while people can think of some further questions. I admit I forget exactly who mentioned this and I apologize. I want to say it was Andrew, but we're going to find out if I was right or not. So one of you mentioned that this source has been behind the sun for the past few months and that it is now emerging. And there was a very tantalizing mention of some future observations. So I'd love to hear more if you can tell us anything about those future observations in terms of like what facilities you hope to use, if you have any predictions for what you think you're going to see, and especially what you hope to learn from those future observations.
Yeah, sure. So it was me who said it, indeed. And so it's really exciting to get back on this source after, 3 months of being unable to observe it. And so there are a range of facilities, so more or less everything on the ground that can see it is now starting to look at it again. But I think what we're particularly excited about is some teams who've managed to get time on Webb and on Hubble. And so one question that we hope to answer with the Webb observations is whether or not there is a supernova there at all. And if so, what sort of elements was it creating? And so it turns out that most of the elements like the carbon and we burn and the oxygen we breathe are made in normal supernovae. But there's an open question about where the very heavy elements come from, things like gold and platinum and uranium. And we know now that some of them are made in the mergers of neutron stars, that we've learned that from gravitational waves, which people may have come across. But there are challenges with that interpretation, and another very promising location for them is in long duration gamma ray bursts. And so now is the time to go and look for some of those signatures. So really, I think the most exciting questions from my perspective are, was there a supernova? And if so, did it actually make any of these heavy elements?
I'll add something there, which is there's another key measurement where I actually think we have the observations. We're just waiting for the results to be finalized and come out, where it's called radio interferometry. You could combine observations from multiple radio telescopes to get insanely precise spatial precision for radio emission. So the jet is initially super narrow. As it's going out, it's building up a shock with the surrounding material, and it's widening over time. So it starts very narrow, and we should actually be able to see the jet itself expand radially. And I think that'll be a really key measurement related to what Kate was answering on trying to understand exactly the structure and collimation of this jet and see if we can figure out how that could have occurred.
There's another question in here from Ethan. It says it's for anyone, but maybe Eric. Do we have any idea how intrinsically bright this GRB is and how it compared to other extremely energetic GRBs in terms of total energy / power output, like GRB 080319b? This may be the brightest burst of all time, but is it the most energetic or powerful?
Yeah, I could take that, Ethan. That's a great question, as always. So we knew immediately at Earth this was the brightest one we had ever seen. In Andrew's group and some others gave us the redshift. When you account for how bright it is at Earth and how far away it is, you can then measure the intrinsic brightness of the gamma ray burst. So the approximate measurements there tell us that this is also intrinsically the most energetic gamma ray burst in the prompt phase that we've ever seen. And we thought we may be able to explain that away. Perhaps this is an observational bias. If it is, the burst is very nearby for one. If it was super far away, perhaps we would miss some of the emission. But even accounting for that, simulating what it would look like at those distances, it is still the brightest one, the most energetic one we've ever seen. And I don't think we have a great explanation for that. The peak luminosity, so not the total time integrated emission, but just the shortest brightness, is not the record. It's only the 99th percentile. But part of the answer is what Kate said, where it looks like most of the energy is very narrowly collimated. So when you account for that, it brings it more in line with the total energetics we've seen from other gamma ray bursts. Whether or not it is the record, when you account for that collimation effect, that geometric effect, we still don't know. So this is part of the remaining work we have to do. But it does seem, if it's not the record, it's still very close to the record there as well.
I'll just add on a little to what Eric said, which is that, as Eric mentioned, measuring precisely how narrowly collimated this jet is critical to understanding the overall total energetics of this event. We have an estimate of that from the measurements we've had so far, but this afterglow phase is going to continue to remain detectable with radio and X-ray telescopes for months and years to come. And if we continue to observe it out to very late times, that should hopefully get us a better estimate of the precise opening angle of the jet. And then we'll have a better understanding of its overall energetics. In the afterglow phase, it seems currently fairly average in terms of the overall energetics for a gamma ray burst, but it is just so bright in the X-rays and even in the afterglow phase because it is so narrowly collimated, we think. Yes, future observations should help to shed even more additional light on this still open question.
Great. I've got a couple more questions if there are none others currently queued up. The first one is just kind of a basic background question about gamma ray bursts in general. So in the 50-odd year history of gamma ray burst science, how many have we observed? Like when we say this is the brightest one we've seen so far, like put that in context. Are there only 2 others? Are there dozens, hundreds? What are we looking at?
I can start, others can jump in. It's more than 10,000. The exact number, we're not exactly sure. I think it's something around 12,000 is how many we've seen. The 2 largest samples come from CONUS Wind and Fermi GPM, which have each seen about 3,500 bursts. And it was both of those teams saying, basically within a few hours of the burst, saying that this is the brightest one we've ever seen, that really got stuff going. So it's certainly 1 in 12,000.
Great, thank you. And so my second question, completely unrelated from that, going back to this supernova that hasn't been seen. So I know that there are 2 main causes for gamma ray bursts, neutron star mergers giving rise to those short duration bursts, and then the supernovae associated with the longer duration bursts. But there is some overlap between those 2 groups. Is there like any slim chance that this is just a super weird neutron star merger and that's why we're not seeing that supernova?
Good question. And so until about a year ago, I probably said, no, there's not. But actually some results that have come out in the course of the last year have in fact shown that there is another very bright, not this bright, but very bright long duration gamma ray burst, which was actually not associated with a supernova, but was associated with this faint radioactive glow of heavy elements. We call it a kilonova. This one doesn't look particularly like that one, so I would say probably not. But there is clearly a possibility, and in particular because the afterglow here was so bright and was outshining everything, getting to those signatures which are perhaps 10 or 20 times fainter than the supernova signature is really hard. But so for the minute, I think my bet would still be that this is a massive star. If the next set of observations really don't show a supernova, then you're starting to be interested that maybe this was. And that would be even more strange because these short, well, you know, they normally call them short gamma ray bursts. These merger gamma ray bursts are typically much less energetic than the collapsing star gamma ray burst. So if you got the most energetic, the brightest burst ever from one of those, that would be truly remarkable.
Yeah, that sounds like I would be hearing about that in a future press conference for sure. Excellent. All right. Just want to ping our journalists. If you have any lingering questions that you want to ask, this is your chance. Give that a few seconds, but if not, we can go ahead and wrap things up. I want to thank all of our presenters for your excellent presentations, introducing us to this exceptional gamma ray burst. For those of you watching online, there is a NASA press release that is now live. You should have seen that in the Zoom chat. I'll also be posting that to the JWST Press Office Twitter account, so you can find that there. And shortly after this meeting adjourns, I will be adding our presenters' slides to the Head 20 press page, and the YouTube video of this press conference will also be archived on the JWST Press Office YouTube channel. So thank you again so much for your attention and for your presentations. And we will see you all next time for the next time a gamma ray burst does something exceptional.
Thanks, everyone.